we welcome Ahmed, who will tell to us about black hole disappearance. Hopefully we'll be still here after the talk.
Thanks, Juan. So, thank you, Juan, for not starting the timer. Okay. All right. Thanks a lot, Juan, and thanks for the chance to give this talk. It's a real pleasure. It's great to see a lot of friends in the audience. So I'm going to talk about black hole disappearance. This is work in progress with my graduate student, Shadi Ali Ahmad, and my two excellent postdocs, Simon Lin and Shoy Ouseph. I should take this opportunity to advertise that Simon is, he's not this big, but he's on the job market this year, and he's very excellent. If you like what I'm going to talk about today, you should, even if you don't like it, you should hire him. Okay. So the first quarter of the 21st century has witnessed intense progress in quantum black hole physics. The prevailing paradigm is the central dogma of black holes, which says, as observed from the outside, a black hole behaves as a quantum mechanical system described by a Hilbert space of dimension e to the s Bekenstein-Hawking, evolves under a chaotic Hermitian Hamiltonian, and interacts unitarily with its environment. These properties are ensured by many things, by the classical dynamics of Einstein's equation, as well as both perturbative and non-perturbative effects in quantum gravity, with most of the heavy lifting done by spacetime wormholes sourced by the gravity path integral. This progress is mostly limited to macroscopic black holes. Not much is understood about black holes that reach the Planck regime and how they eventually disappear. The question that I would like to answer in this talk is what happens at the end of black hole evaporation? Here's a picture that Stephen Hawking, or cartoon rather, in one of his papers, and actually I think it's the pair creation at the horizon paper, and where he says, the matter that runs into this region, namely the singularity, might re-emerge in another universe, or it might even re-emerge in our universe through the upper vertical line, thus creating a naked singularity. The second scenario received much attention in the 90s, for example, in an analysis of the CGHS and RST models, where the hope was to see this transition in the perturbative or G-Newton expansion. And I would say that that body of work, while very interesting, was largely inconclusive regarding this question. Here's a quote by one of the experts. I will let you read it. Namely saying that the relevance is not quite clear yet. There's been some speculation in the literature of the first scenario, namely where the interior or things that fall into the interior re-emerge in another universe. In this talk, I will motivate this picture through a two-dimensional model. I will consider a modification of JT gravity that has black hole solutions or black hole states at high energies and horizonless solutions at low energies, and provide a mechanism to go between the two. So these are going to be some of the pictures I will draw. This is a black hole in this model. This is a state with no horizon. And here is kind of a picture of what the analog would be of the red scenario in this model. Here's the outline of the talk. I will begin with a review of JT gravity, then give you a paradox involving islands. I will set up an evaporating black hole and analyze what happens. And then I'll transition to the role of wormholes to give a complete picture and how that paves the way for complete semiclassical evaporation of the black hole. And then end with some comments and conclusions. So let's start with a review of JT. So one way to think about JT gravity is in the so-called boundary particle formalism. JT gravity describes a two-dimensional theory of gravity with a dilaton phi and a metric g with negative cosmological constant. It can be obtained from a higher dimensional reduction where the dilaton acts as a transverse area. After imposing the right kind of boundary conditions on the metric and the dilaton at infinity, the single dynamical degree of freedom is a reparameterization T of u between the bulk coordinate time t and physical boundary time u. And this reparameterization determines the shape of the boundary with a putative holographic dual lives in the limit as it is taken to the boundary. So the physical boundary are the red lines, and u is the physical time coordinate running along these red lines, and t is the bulk coordinate. Let's go over the equations of motion and solutions of JT in this formalism. So the Lagrangian of the theory is, or rather the Lagrangian of the reparameterization mode is simply the Schwarzian derivative of that mode. The system has time translation symmetry, whose conserved charge is the ADM Hamiltonian. It's given by the Schwarzian derivative, again, of the reparameterization mode. And the equation of motion in this theory is simply energy conservation. Just the time derivative of the energy is equal to 0, which can be recast in a sort of geometric description as saying that the extrinsic curvature of the boundary world line, that red line that I drew, is constant. The derivative is 0. In the Lorentzian theory, this equation applies independently for the left and right reparameterization modes. So let's focus on the left reparameterization mode for now and discuss what the solutions look like. So here's what a positive energy solution looks like. This corresponds to a near extremal black hole. And these dotted lines are the horizons from the perspective of the left side. Zero energy solutions look like this, just extended black holes, extended up to the point where the horizon hits the other boundary. This is simply the Poincaré patch, which you can think of as an extremal black hole. Other solutions that are not talked about much are negative energy solutions, which are actually horizonless. These are given by reparameterizations or shapes of boundary trajectories that never hit the asymptotic boundary. So the way you find sort of complete solutions is you need to find a solution for both the left and right boundary particles and then combine them. However, not all combinations of left and right boundary reparameterization solutions are physical solutions. Physical solutions are only those with vanishing total SL2 charge, Q left plus Q right is equal to 0. This is the gauge symmetry that corresponds to moving both boundaries together along isometries of ADS2, as shown here, adapted from a paper of Lin, Maldacena, and Zhao. So let's go through some examples of physical solutions and non-physical solutions. So here are two physical solutions describing just an eternal black hole, where the horizons of the two boundaries meet. These two are essentially just SL2 transformations of one another. Some examples of non-solutions are where the horizons do not meet. So they miss in this way, they are separated from one another, or they go past each other, or for example, combinations of these horizonless solutions. Because of the reflection symmetry across the vertical axis in all of these non-solutions, the excess charge, which has not been canceled, is just a global energy, the charge corresponding to this symmetry. To make these solutions, we can make these solutions by adding matter. So matter in JT gravity, the simple kind that we like to work with, is matter that does not couple to the dilaton. In that case, the matter talks to gravity only through the gravitational constraints or the SL2 constraints. It just lives on a background ADS2. The matter Hilbert space organizes itself into representations of SL2R. Here's an example where I diagonalize the global energy E, and where the boost and the momentum act as raising and lowering operators. Physical solutions are then singlets of the entire system, the left boundary plus the right boundary plus the matter. So the sum of the three charges has to vanish. And what the matter can do is that it can soak up the excess charge in the left and right of the left and right boundary particles. Here's an example where positive matter global charge supports this long wormhole where the horizons are separated. But for the cases where the horizons are brought closer together, the global matter charge has to be negative. Okay? This negative global charge might seem a bit exotic, but there are many ways of generating it. Most famously is by the double trace deformation of Gao-Jeffers and Wall, where you couple the two sides by some simple operators, or by switching on imaginary sources for massive scalar fields as analyzed by Garcia and Gautier, and also by Maldacena and Chi, where this is kind of morally the same as the first one, where you consider you have a bulk matter theory rather, or for example, a bulk matter CFD, but where you impose periodic boundary conditions. So from the matter CFT's perspective, this line is identified with this line, so it lives on a cylinder, and the Casimir energy plays the role of the negative matter global charge. The details, so in this talk, I'm going to assume I have negative energy. The details are not going to be important. All right, there's another convenient formalism, which will be convenient for us in this talk of JT gravity, which is that of a particle scattering off an exponential potential. The particle represents the renormalized geodesic length between the two boundaries. The left and right boundary Hamiltonians in this length basis makes the interaction with matter manifest. The Hamiltonian, so it's a function of the length and the conjugate momentum of the length, but also the SL2 charges of the matter. So you can see the interaction explicitly. Enough for our purposes will be to consider the classical limit of the matter theory, which allows us to pick specific values for the three non-commuting SL2 charges. So we pick the momentum and the boost to be 0, and we keep the global charge general. This Hamiltonian is the Hamiltonian of a one-dimensional Morse potential. And depending on the sign of E, the potential looks very qualitatively different. For negative E, you generate a dip, which means you can have bound states in this theory. So let's analyze that theory more. So the theory with negative global charge has two qualitatively different kinds of states. States with positive energy are scattering states, where the length begins at infinity and ends at infinity. These are black holes that are made temporarily traversable by the negative global matter energy. So they look like this. A signal can be sent from one side to the other, but not for all time. The length here goes from infinity to some finite value back to infinity. These correspond to positive energy solutions as shown here. As the energy gets lower and lower and lower, the solution becomes two completely overlapping Poincare patches. Negative energy states are bound states, where the length mode remains finite. These are horizonless, so-called eternal traversable wormholes that allow eternal communication between the two boundaries. All right, so that's going to be the model that I'm going to work in. And now let me give you a paradox. The question is, what is the fate of the island in this model? Suppose we start with a positive energy state, so a black hole, and couple the system at some time to an external bath at 0 temperature. As the black hole evaporates, an island will be generated. However, when the system eventually reaches the ground state and becomes an eternal traversable wormhole, there's a question of what happens to the island. This is non-trivial because if the system smoothly transitions in this way to an eternal traversable wormhole, it leads to acausal signaling. acting with a PETS operator on the radiation arbitrarily far away, you could have even decoupled the system before you did that, allows you to send a signal to the boundary through the island in a very short time. One way to get around this is to say that this picture is wrong, and the right picture is something more analogous to Hawking's second scenario. That maybe the island is stuck inside of the horizon, as in there's a singularity that happens in the bulk, that gets created in the bulk, and the island is stuck in its past. However, this picture is not satisfactory because it would suggest that the space disconnects and seems like it precludes reaching an eternal traversable wormhole. The point of this talk is to resolve this puzzle. All right, so now let's actually study what happens to evaporating black holes in this negative global charge model. So let's consider JT gravity with negative matter global charge. Again, where the negative global charge comes from is not important. On top of this, we can add a 1 + 1 dimensional CFT that extends into an external bath through transparent boundary conditions at the boundary, or rather at the boundary particle. On the right panel here, I'm showing you the Penrose diagram of the ground state. So this is a static eternal traversable wormhole attached to a 0 temperature bath. More generally, the shape can be very different, and the dynamics is then governed by the conservation of total energy, namely balancing the flux through the boundary with the derivative of the ADM energy. So this is a flux flowing into the ADS2 region. Okay, so let's talk about black hole formation and evaporation in this model. So we're going to start with the ground state, so the eternal traversable wormhole. And then we can form a black hole by throwing in a shock wave and then letting the black hole evaporate. We choose a setup that is symmetric between left and right, so we can just focus on one side. To set up the equations, we need to find the quantum stress tensor of the matter. And the principle for assigning a matter stress tensor is to take the initial state to be the vacuum in the flat bath metric. The stress tensor in the future will then be determined by the reparameterization and the transformation property of the stress tensor on the Weyl transformations, or rather just a Weyl anomaly. This is a technical comment. The resulting equation of motion is the following. Let's break it down. On the left is just the time derivative of the energy. The first term on the right is the stress tensor that is generated by the reparameterization. The second term here is the energy of the ingoing shock wave, and the last term is the energy of the outgoing shock wave up to a redshift factor as it comes out. For this talk, I'm going to ignore the last term. Okay, so you should think of this as the shock waves go in, the matter goes in, and then gets stuck inside the bulk. Okay, so how do we analyze this equation? Well, we were unable to solve these equations analytically. However, they can be solved in an adiabatic limit where the evaporation is slow. This is the regime where the central charge times g Newton, or 1 over the renormalized dilaton, is very small. Practically, this means that you take all time derivatives to be small. However, there's a subtlety. The equation from the last slide is 4th order, meaning that the phase space is labeled, not if labeled, is labeled by 4 numbers, the conventional choice being t, t prime, t double prime, and t triple prime. This is not a good choice of variables because we're not actually allowed to drop these higher derivative terms. Even though, for example, t prime can be small, t double prime and t triple prime can be large. A better basis to work in is using t, the reparameterization, and the 3 SL2 charges of the boundary particle B, P, and E. Those 3 charges are functions of t and its derivatives. The adiabatic approximation is then implemented by requiring that the time derivatives of these charges are much smaller than the charges themselves. We pick an adiabatic ansatz where the reparameterization is an SL2 rotation of a non-evaporating solution. At every instant in time, it looks like it's a non-evaporating black hole. So it's an SL2 transformation of e to the ku. E to the ku is the solution of a static black hole, where k is the square root of the Hamiltonian, which happens to be this combination of the charges. There are many constraints between all of these variables. Okay, now let me give you the results. So we find qualitatively different behavior depending on the sign of Hs plus Hg, where Hs is the energy of the shock wave and Hg is the ground state energy of the initial state. Recall that the ground state energy is negative. Yeah, so we started with an eternal traversable wormhole, a static eternal traversable wormhole of negative energy. Let's consider the case below threshold. So Hs plus Hg is less than 0. When you throw in the shock wave, the energy suddenly rises, but it's not enough to change the sign of the ADM energy. What happens is that the system, it does evaporate, it loses energy, and it oscillates down to an eternal traversable wormhole, but at a higher energy than the original ground state. Why this happens will be clear in a moment. And so the picture looks like this. So we start with the eternal traversable wormhole. It rings down, there's a shockwave that comes in, it excites it, and then it loses energy and goes back to a static eternal traversable wormhole again. We compare these numerics to the adiabatic approximation, and we find excellent agreement. The way we solve this problem is we first notice that that you can break up the solution into a slow mode and a fast mode. So we break up the energy, or the square root of the energy, into a slow mode k and a fast mode k, and then we integrate the equations against one period of the fast mode, resulting in an equation for the slow mode, which we solve, whose solution looks like this. So it's some constant plus an exponentially decaying piece. There's something very interesting about this solution is that it exhibits some universal late time behavior. The constant piece is independent of the central charge of the matter theory. So it seems like it's independent of the way that we couple to the bath. We're trying to understand the implications of this better on general, on thermalization in general. Okay, so that was the case below threshold. Now let's look at solutions above threshold. So in this case, black holes are formed. These are positive energy states. And what happens is that these black holes evaporate down to zero temperature. So it evaporates down to a Poincare horizon, which you can think of as an extremo black hole. And the adiabatic solution we find is essentially just exponential decay in time. There's some transient thing that happens at early times. Again, we find excellent agreement with numerics. The surprising thing here is that the system fails to find its ground state. So as I said, this is surprising, and it's kind of reminiscent of a remnant. So you started with a black hole, a system with a horizon, and it doesn't seem to be able to sort of get rid of its horizon or of its interior. So what's going on? To understand what's going on, we have to track how the Hamiltonian of the length mode is modified by the shock wave. What the shock wave does as you insert it, it doesn't just increase the energy, but it also contributes to the bulk matter global charge, and therefore it can remove bound states. So it contributes to this term, and it can make it positive. And in that case, you remove these bound states, and therefore it's not surprising that the evaporation will just take you down to zero energy. I should say that as the black hole evaporates, the global charge does or is slightly reduced just by the evaporation itself, but it's not enough to change the sign. This is actually a statement of the ANEC. If you consider the case of just an eternal black hole, no coupling, no negative energy, etc., and then you allow one side to evaporate, that shouldn't make the black hole traversable. It's that statement. So the system seems to get stuck in something you might call a false vacuum. And another important comment is that since the global charge is conserved at the disk level, perturbative quantum effects cannot help you. So no matter what quantum effects of the length variable you include, you will never change this potential. So perturbative quantum effects can never transition you back to the actual true ground state. What is needed are non-perturbative effects. That brings us to wormholes. So wormholes famously violate global symmetry. So the emission of a baby universe can extract some of the global energy and deposit it in some baby universe. Wormholes or baby universes effectively then generate non-vanishing overlaps between states of different global charges. So here's an example of the overlap squared of a state with a shock wave and a state without a shock wave. If you slice this diagram, you have a picture like this, which allows for non-zero overlap between states of different charge and different length, because that can be soaked up into the baby universe. And so the effective picture is something like this. As the system evolves, the global charge is emitted into the baby universe. See, there's actually a paper appeared last night by Saciasta Swingo and Pilar Lopez, some of who are here, on precisely this process and how it helps you transition in the Moldesine-Chi model from a black hole to the eternal traversable wormhole. But there's a problem. By unitarity, it is equally likely for this process to both lose or gain charge, right? The amplitude to raise the charge must be the same as the amplitude to lower the charge. To generate a bias in one direction, we need dissipation, which in this case is evaporation, and to note that wormholes preserve the total energy. They preserve the overlap matrix of ADM energy eigenstates at infinity. Overlap of this is always a delta function. And the way to think about this is the wormholes act deep in the bulk. They don't affect the boundary conditions far away. So the claim is that these wormholes can then pave a path to complete evaporation, and let me walk you through the steps of how that would happen. So say we start with the ground state. So this is in the model with negative global charge and some negative energy. So we're down here. We throw a shock wave to form a black hole. So now the energy is positive and the global charge is positive. We then allow the system to evaporate. It will evaporate down towards a zero energy black hole or the Poincaré horizon, but maintain the charge to be positive. Every now and then, baby universes will be emitted, and as a result, the global matter charge can change. And suppose it changes in the right direction, where the energy goes down. Rather, the ADM energy remains fixed, but the global charge goes negative. And then subsequent semiclassical black hole evaporation can simply take you from that black hole down to the ground state. The statement of what dissipation and conservation of energy by wormholes gains you is that you cannot go back. As the energy goes negative, the emission of wormholes that raise the global charge are disallowed because there are no states here of negative energy. So the next step is to actually show you that in a theory with negative global matter charge, semiclassical evolution can actually evaporate you down to the ground state. So starting with a positive energy solution with negative global charge, we need to show that a black hole evolves down to an eternal traversable wormhole. And so the way we do that is we consider an eternal, we consider a temporarily traversable black hole, and then which we quench at some time and allow it to evaporate. So what we find is that in these kinds of states, the matter stress tensor is peaked near the origin, and therefore when it is quenched early enough, the system energy rapidly goes negative and the horizon is lost. And to address the paradox that I discussed earlier, in this case, the evaporation is so fast, we don't expect an island to form. Essentially, that's just saying that there's no horizon. This resulting state after the transition is in some sense a white hole. So what the baby universe emission does is that it transforms black holes to white holes. I've missed a citation here to work of Douglas Stanford and Zhenbin Yang. Some work in progress. It would be good to have all of these steps incorporated into one model. And this entire scenario can actually be tested using this recently developed method for defining non-perturbative overlaps in JT gravity of these authors. The way that this goes about is that one samples the eigenvalues of a random Hamiltonian giving eigenvalues hi, and then which can be used to define non-perturbative overlaps but using disk-level wave functions. Then, if you have these wave functions and overlaps, then you can define a density matrix of a black hole. Say you start in the positive global charge sector, and evolve it using the Lindblad equations. So we can actually do this. We can implement this using Monte Carlo. We already do this, but I don't have clean data to present. And what happens is that the wave function initially spreads. It spreads on all possible values of the length and matter global charge. But eventually, the probability gradually peaks at the length of the ground state. Okay. Now let me give some conclusions. So what is the higher dimensional scenario here? So the statement is that, say you form a black hole from collapse in this way, there's a non-zero probability that there's non-zero probability that a baby universe will be emitted, and subsequent semiclassical evolution has to be started with the state after the emission of the baby universe. So in some sense, the space-time picture you're supposed to consider is not this, but this. You evolve to this slice, and then you continue from the purple slice onwards. Interesting thing here is that it kind of says that the singularity is kind of just an artifact of starting with these slices and then evolving with the semiclassical equations. And they're kind of a red herring. But to be sort of for full disclosure, even in this case, one expects that the singularity that there's a singularity inside of the baby universe. Let me give some further comments. For consistency, this process must respect the second law of thermodynamics. In the case that we discussed, we had a zero temperature black hole of entropy S naught, and when it transitions to the eternal traversable wormhole, there must be a way for it to shed. Whoops, to shed, not the talk. to shed all of the ground state entropy. Oops, why is it not showing? Sorry. Okay, good. So the black hole must shed away the ground state entropy S naught, and it must do so with only a few quanta. This can be done if we think of the late-time black hole as an unstable atom with a decay amplitude that scales as e to the minus S naught. The timing of this transition is Poisson distributed, can happen at any time, with a transition rate of e to the minus S naught. And as a result, the final radiation will come with a large entropy from timing uncertainty. That's just a statement that the Shannon entropy of this distribution goes as S naught. Second comment is, from the parent universe perspective, the black hole singularity was removed by the baby universe. Can we think of this as a bounce scenario? Does this apply to cosmological singularities? I don't have an answer to this question yet. Okay, so just to conclude, here are the takeaways. So we saw that non-perturbative effects are needed for black holes to disappear. Otherwise, they get stuck in a remnant. And the key was global symmetry violating wormholes that provide a pathway for semiclassical evolution to reach the ground state. And so this picture beats this picture. Thank you.
Yeah, thanks for a nice talk on that. You made this assumption that you could ignore the outgoing shock wave. What's the regime in which you expect that to be true?
Okay, let me say two things. First is that none of these conclusions change if you account for the shock wave going out. Second comment is it depends on the details of the matter theory you're considering. If the matter theory has no interactions, these are just free fields, they will just go through each other. So you can consider a case where you do have interactions where you expect that these two shock waves might, get stuck.
Sorry, yeah. My worry was that that it might spoil the fact that you found that the central charge dependence vanished. But you're saying that doesn't happen.
Good. So in the case, okay, again, let me say two things. In the case where a black hole does not form, just the fact that they exit the ADS region does not mean that the global charge all disappears. Global charge is measured differently than asymptotic energy. That's one comment. Another comment is, when you form a black hole, even if they go through each other, they get stuck behind the horizon. So they actually don't escape in that scenario.
Okay, thanks.
In 1974, Erdely argued that a white hole is unstable and would become a black hole because you could have small energy perturbations that are enhanced by the redshift near the white hole horizon. Can you comment about such an instability in your set?
I don't know if we can see it in this setup, but I don't think that precludes the energy from gradually going to zero after a sequence of non-perturbative effects. So maybe it forms a white hole, then becomes a black hole again, but then it's going to form a white hole again, and so on and so forth.
Can you comment a bit more about the model you use quantum color using the model you use quantum color to simulate? Like what kind of model is that?
So we had to make some assumptions about what the Lindblad operators look like. So assumptions we made, there's a generic choice that follows from formalism by somebody whose name starts with G. Forget his name. Maybe somebody knows. Okay, I don't know. So we choose Lindblad operator. So we take the bath to be at 0 temperature. That makes the choice of Lindblad operators very simple. They only go in one direction. So we pick a model like that.
Just very quickly, what are the timescales involved in sort of this final step towards the evaporation?
So let's see. So the time scale for this to happen is e to the s. Yeah. But then after that, it's a very short time.
Thanks for the nice talk. If in your work in progress slide, I think you mentioned that you have a non-perturbative JT version of this with some matrix model dual. I was wondering, so in the dual of the usual Mandelsina-Cesari, you need a coupling between the SY case. So what does that look like in the matrix model study?
Yeah. So here we consider the toy model where we mock up the coupling by adding a negative tension particle or negative mass particle in the bulk. So you can literally just take the wave functions of JT on the disk with a positive mass particle, and then just continue the mass to go negative. In fact, when you do that, you can even see at the level of the spectrum of the theory that these bound states emerge. There are some poles in the complex energy plane of in the form of the density of states, and they cross the real axis as you continue the mass to go negative. So more about that later, but you literally take the positive mass wave functions and you continue them.
So on your final slide, you said that your conclusion is that the baby universe picture wins out over the universe splitting in half picture. But I'm a little bit confused why you concluded that, because in any UV completion of this theory, you have end of the world branes, and you have an instanton to tunnel like the left picture. Have you calculated anything with that? Do you know if that competes or wins out or anything like that?
Well, so in this model, this is the process that makes the black hole disappear. We don't see any indications of something like this. We never had to worry about what this junction here means, attaching this singularity to the r equals zero slice. There's also the issue that this suggests that the final state won't be the eternal traversable wormhole because it looks disconnected here. Let me add one more comment. In some sense, you can think of these pictures as being the same thing if you, by hand, say that this picture is this picture, provided that you identify this line with this line. And so then kind of that the singularity sort of comes out of the board and it pinches into a circle and then becomes this closed universe. So those are the comments I can make.
Yeah, so you mentioned this singularity as a red herring from the perspective of a parent black hole. I wonder, let's say, what does they say about experience of someone jumping into black hole, especially at early time, let's say. I understand that bulk time and boundary time is different, but still, does it in any way modify the observer's experience depending on if the black hole is evaporating or not?
So if an observer falls in and enters the island of the radiation, then they have to end up inside of this baby universe. And I'm hoping to understand what happens to them from your talk.
I had a question related to this. So you mentioned in the singularity that there is some kind of bounce, but normally when people talk about the bounce, it's the bounce for someone who goes into the black hole interior, and then that singularity that naively is there then bounces. But this discussion would force you to, well, I mean, in order to translate it to this discussion, it would be a bounce for the person who lives inside the baby universe. That's the same observer that Ying was asking about. And I think from your talk, it doesn't follow that these bounces. So.
Yes. Yes, an observer that is here will not be here and come out. Yeah.
I can make baby universes with different sizes. I guess in JT, they always come with the same suppression, but in a more realistic situation, should I expect it to be this process to be dominated by production of many of those smaller ones rather than one big one?
So I don't have details about what type of baby universes dominate this process, but it has to be baby universes. It could be one, could be two, could be many. In this model, they're suppressed by e to the minus s naught. So e to the minus the entropy of the black hole. So for more realistic black holes, once they reach the Planck scale, there's no suppression for generating these baby universes. So they get amplified as the black hole gets smaller. And it could be order 1 when it's Planck scaled.
I guess maybe you could comment on the time scale for the evaporation of the 4D case versus.
I think in the 4D case, it's not going to change by much.
You don't expect it to be 2DS.
No, right. It's going to be, I think it's not going to change by much compared to the usual 4D evaporation timescale, because these effects will come in when the black hole is Planck scale.
Have you thought of what this baby universe emission operator change the ADM mass? So it gives you non-perturbative crashing of the ADM mass because of the baby universe change. And then what's the effective potential?
I have not thought about that much. Well, I guess what I would say is that okay, no, let me not say anything.
Let's thank Ahmed again.